I'm going to talk about the issues behind air safety, primarily in the context of commercial air transport, because that's where most people come up against aviation most of the time. If you're nervous about flying, then I'll start by saying that air travel is one of the safest forms of transport in the world. But I'll also point out that for us to understand why it's safe, we have to talk about some of the accidents that have happened. So I'm going to talk about accidents and describe what went on behind those. And from those, we'll learn how it is that it becomes as safe as it is today. I hope. Tim's already mentioned where I come from. I was a Royal Air Force fighter pilot, became test pilot, traveling from fighters into big aircraft, and then with industry doing a very similar thing. And also, actually, my last first flight was as the pilot of an unmanned air vehicle, so I kind of encompass most of the things that we do. I should point out that this is my view. It's not all the view of anybody that I might represent elsewhere. But I'm going to talk about regulators, because they are supposed to regulate what a safe flight requires and how safe really is flying, and then summary and questions if I've got through in time. I'm sure I will. Very briefly, regulators ICAO, up in the top left-hand corner, based in Canada. They were formed in 1944, actually during World War II, when the Chicago Convention was signed. They now have 100-plus member states, and actually it's about 150. And they coordinate and come up with good ideas that they think internationally should be applied. The states then decide whether or not they agree with them, because ICAO has no executive authority. And ICAO issues recommended procedures and standards, or SARPs, and they've got about 10,000 of those. Individual countries take as much of that or as little as they want. We are trying to persuade them to take everything so that everybody does aviation in the best way across the UK. We have two major regulators, EASA, European Aviation Safety Agency, Authority rather. There are so many, unfortunately I only ever talk in letters, I don't ever have to say them out in full. EASA look after the European Union effectively and one or two other states, and the FAA, the Federal Aviation Administration, who look after the American bloc. There are other countries like CASA in Australia who have their own national regulators, but by and large, almost the whole of the world either does as EASA and FAA or copies EASA and FAA. So we have a pretty cohesive set. I'm going to come back to them as we go through in a moment. If I press the right button, that is. So, what does a safe flight require? It needs to be a safe air vehicle flown in a safe environment. And it needs to be flown by a safe crew, operating to safe procedures and supervised by safe management. Now, that's not my idea. That's a construct that came out of the BAE Systems Corporate Flying Standard. That construct works for safety, whether you're an airliner, a fighter, an unmanned air vehicle, and it actually works for everything that that company does globally in all its different forms and guises. So we'll look at each of those in turn. I'm only going to be able to glimpse across each of the topics, I'm afraid. I could do 3 lectures on each of those individual subjects, but time today won't allow me to do that. So if we look first of all at the safe air vehicle, another subdivision, I'm afraid, we need it to be designed, manufactured, maintained, and then prepped for flight safely. And each of these bring their own particular challenges. When we talk about design, the designer will always start with the end in mind. So our airliner is going to have to fly high because that's where our jet engines work most efficiently. It's also cold and low temperatures, low temperatures and low pressures up there. But we need the people inside to be warm and not to have to wear oxygen masks while they're flying. So that will put some particular stresses on the aeroplane. It needs to be strong because it will have to fly through turbulence. It may get hit by lightning. And when I mean turbulence, I don't mean the sort of turbulence that most people say, oh, we got bounced about in our aeroplane. If you have severe turbulence, the cabin crew and the trolleys will leave the floor and hit the ceiling. That's what severe turbulence is like. So most of us in here, I would guess, have never, ever experienced really severe turbulence. The designer knows what it's like, and then having calculated the stresses that that puts on the aeroplane, applies a 1.5 factor, because that's mandated by the FAA and by EASA, as a safety factor, and builds that extra strength in. So if, like my wife, you're worried about the wings falling off every time you fly through light turbulence, that's not going to happen. Also looks at the whole of the operating environment. We'll skip that, but we'll go to reliability, and this is particularly important. By design, you must not have a single failure that could lead to a catastrophic event. By design, you cannot have a single failure that would then create another failure that would cascade into another set. And those are laid down by FAA and by EASA in their specifications. The FAA have about 1,800 different itemized things that you must check the aircraft design against. One of them covers the locks on the cargo and passenger doors. One of them actually covers the lock on the toilet door. They go down to all sorts of unusual detail. But if we've got our design right, now we've got to manufacture it. And our designers and the company have a vested interest in the safety of the aeroplane, because otherwise the technical director goes to prison, probably with some of the other board members. The manufacturing team will be multi-skilled, large number of people, probably working shifts under tremendous pressure, because now the design is finally delivered. They've got to get it all put together on time. So there's always a little bit of a temptation for the people in the manufacturing teams who are trying to turn paper, or more often these days, a computer screen design into reality by bringing all the bits together, to just make it work. And this is where culture comes in, and you may be surprised, but I'm going to spend a lot of time talking about culture as a safety enabler in aviation. If there is no good rapport between the people who are going to build and the people who designed, then when you have an issue, and it still comes up even with computer-aided design, where a part doesn't fit, probably because the engineering tolerances or something, minor issues actually turn into the bit won't go in. There are two ways to resolve the part doesn't fit. One is you go back to the design team, you say the part doesn't fit, we need to work out why that is, fix the problem so that this particular aeroplane and every aeroplane that we build after this is okay, or you have the quick fix, which is a big lump hammer, and you bang it until it actually goes in. And that will get the part in place, but probably you'll have a failure further down the line, either in final build test or when the test pilots take the aircraft up, just to make sure that it's all working properly. So the culture that allows the people who are building to go back to the designers, and indeed to go to their management and say, sorry, I can't do this. I know we're on a tight schedule, but we have an issue here that we need to be resolved, is where company culture really comes in. Now, in the old days, we thought that people were either perfect or incompetent. And if you made a mistake, you were incompetent, and therefore your best defense was to cover up the mistake so you didn't get fired. These days, we're trying to move everybody into a different place entirely. What's now called just culture, which is a culture where when you see something that's wrong, you can say, I spotted this, or I've made this mistake, and the organization then goes, instead of you're fired, they go, okay, let's understand why that mistake occurred, what are the factors behind how that came about, how do we fix them, and then we make sure that everybody else knows that that's how we make things better. That's a just culture. It's not a no-blame culture. Just culture means that you behave in the way that I've just described, but if you cover something up, then you are out. Because the worst thing that you can do is to hide something that is not going correctly on the aeroplane. So culture plays an important part. Configuration control does too, because this team is bringing all sorts of different bits together. There'll be hardware, software, all sorts of things. Now with hardware, that's great. I've got a box, I've got a number on the side, I've got a hole to put it in, it fits in okay, I've written the number in my little book, and now that I know that that part's installed. And if I'd forgot to install it, somebody else would notice the hole. With software, it's different. It arrives on a computer, or it's going to get squirted into the aeroplane by one of the people who are building it on an upgrade program. And the only person who knows it was squirted in is the person who squirted it in, because you can't see it. You can't touch it, can't feel it. And even the person who squirted that software into the aeroplane may not know what that software was because someone else probably loaded his loading device. So the challenge for today's manufacturer is to make sure that you have really tight control on the software that goes into your aeroplane, that the software is correct and correctly written, and you really knew exactly what it was that you got. The latest media reports, and I'm not going to validate that or otherwise, on the A400M accident would suggest that that was an issue of software. Finally, when the thing's built, we put it up to production flight acceptance test, which is effectively the final quality control status where the test pilots go off, make sure that everything's okay, and say, yep, you can deliver it to the customer. So that's manufacturing. What about maintaining? Because we've built it and we've given it to the airline now, and when maintenance goes wrong, it really hurts. Japan Airlines in 1985 had a 747 that had an explosive decompression of the rear bulkhead. That's the bit right at the back, behind even the rear toilets and the rear cabin. It happened because a routine repair, had not been done properly several years before the accident itself, and then went unnoticed. A maintenance failure led to the loss of the aeroplane because the repair was not done properly. That repair allowed fatigue to build into the rear bulkhead. The bulkhead blew explosively, took out all the hydraulic lines, parts of the tail, and the aircraft crashed with the loss of everybody on board. So doing maintenance correctly is absolutely essential, and it's as essential as building it properly. And inspection, repair, replacement is what I'm talking about when I talk about maintained, and it's done by licensed maintenance engineers who are licensed in a similar way to pilots. It's done to approved maintenance manuals that are written by the manufacturer, and it's done with anything critical. One person does, another person checks, and then they both sign off the work so that it's independent and two-person. So there are checks and balances put in there to stop things like the accident that happened a long time ago, back in 1985, probably triggered by a maintenance error in about 1970, 1980. Again, if you haven't got a just culture in place when people are doing maintenance, because they'll be under pressure to get the aircraft back out and into service, then you don't have a safe culture and you don't have a safe output. So the regulators now look and inspect and demand just culture from maintenance organizations. Having maintained it, we're now going to push it out, get it ready for the flight, and this is the prep for flight. And there are two bits to this. There's a technical, put the fuel and the oil and the other bits and bobs in, and there's the ground handling, which is taking the passengers and the cargo out, putting the new passengers and the cargo back in, and their bags, of course, and the catering. And I could never work out if catering was technical or non-technical. People working in this environment where they can get sucked in one end of a jet engine, blown out across the pan by the back end of the jet engine in all weathers, day and night, surrounded by vehicles driven by people rapidly in and out towards the aircraft. That's a pretty hazardous place to work. And in the 2007, it was estimated that one aircraft in every 5,000 flights was damaged on the ground while it was parked by this particular activity. So getting this right is absolutely important, and you don't get it right by telling the people to be careful. You get it right by teaching them why people make mistakes, what that looks like, how that's corrected, and having the culture in place that says, when we have an issue, how do we make sure that it never ever happens again? So we're back to just culture, but these people now have human factors training packages available for them, actually led by the Dutch for EASA. The crew are critically interested in the weight and the balance. If it's too heavy, it won't take off, so they want to know that it's the right weight, and if the center of gravity is in the wrong place, it won't fly like it should do. And somebody else does that for them. So this is another area where configuration control, making sure you get the right standard of airplane, is absolutely critical. The passengers also introduce all sorts of strange and wonderful devices into the airplane. We all now have iPads, laptops, mobile phones. They all have lithium batteries. Lithium batteries have a failure mode that is most unpleasant. and therefore the airlines have different ways of carrying them and coping with them. And indeed, now cabin crew are specially trained with how to handle a lithium fire. But that does generate, and it has generated over the recent years actually, a new threat to safe aviation. And if you carry safety matches before you smoke, best you read where you must put them if you're going to take them onto an aeroplane. Actually, the real message here is, before you fly with an airline, go to their website. They're all slightly different. Just make sure you've got the right things in your hand and in your hold bags. And the safe environment then starts with the fire section at the airport, because they're configured to be able to get to anywhere on the airfield and start firefighting within 2 minutes, which is a pretty heavy ask. That's why the Americans have really souped up machines. And to bring the fire under control within 1 minute of arrival. So within 3 minutes anywhere on the airfield, a fire should be at least contained. The wider environment is the controlled airspace that air traffic take us through. The green bit here is controlled airspace. It's a map of the RSC with the Isle of Man, for those that really want to orientate themselves. But the green bits is where the airliners go, and the controlled airspace is designed to keep the non-airliners away from the airliners. So this is a question of keeping the area safe. And these were designed, you see here there's a beacon, to go from beacon to beacon. There's another one down here, Pole Hill. So that the airliners in the old days would have a needle on their compass display, and they would tune to the next beacon. The needle would point towards it, they'd fly towards it, tune to the next beacon, and then fly to the next one. That's why airways are constrained the way that they are. Usually about 5, sometimes 10 nautical miles wide, and that was to take into account the variability of the pilots trying to get the needle to point at the correct bearing into the correct beacon. Then GPS came along, and now everybody flies precisely down the centre line of the airway, which means that each airliner is passing directly over the one beneath or above on the air route itself, which poses an interesting question, which is, how close do airliners get to each other? Well, we have an altimeter, and they're really accurate. We've been using those traditionally up to about 29,000 feet, and we've proven that if you stay 1,000 feet apart from each other, about 300 meters, then you're fine. Used to be in the old days you had to be 2,000 feet apart, because as the atmosphere gets thinner, because these measure barometric pressure, or work through barometric pressure, then the accuracy started to decrease. These days, the state of altimetry has improved to the point where we now can operate within 1,000-foot separation, 300 meters vertically, all the way up as high as you're permitted to fly, or typically 41,000 feet for an airliner. Aircraft that have reduced separation at high altitude have special checks made on them just to make sure that they're okay. But that means up and down, we're pretty accurate with what it is that we've got. And then air traffic needs to know where we are, so they started using radar, which does the old send the pulse up, bring the pulse back, and that would give you a splurge on the screen, which was okay-ish in range, pretty awful in angle of return. So they weren't quite sure where the airplane was, and that tended to drive what we see next. We did improve on that, because the pulse used to get returned with another pulse carrying data that would give air traffic controllers all sorts of information. So now they get a track on their display with some extra numbers associated against it, and they were slightly more aware of where we were, but they still had to rely on that real radar return for separation. So while we could be 300 meters vertically, which I think is actually quite close, we do still have to be 2 to 5 nautical miles apart. Generally, it's 5. If you're in London, where the radar's going around faster because everybody's at closer range, 2 miles is not unusual. And in fact, London now control under time as well, because they have some really wacky devices. So if you're in your airliner and you see another airliner coming and it looks like it's going to hit you and it just skims across the top, that's quite normal. Don't panic. If there's a bump, that's the time to start panicking. But you shouldn't spill your gin and tonic just because there's an airliner that passes very close across the top of you. Those pulses that those transponders send can also be used aircraft to aircraft, and they give us an awareness of what's going on around the outside. This gives you, it's actually a vertical VSI, vertical speed indicator, showing that we're flying level. But this shows us that we've got an aircraft, no threat, just a bit of information. It's 1,800 feet above us. There's one 1,000 feet beneath us going down, so they're kind of highlighted. There's one further away. This is a 6-mile scale, so this is a 2-mile ring. There is an aircraft 200 feet beneath us, which is not permitted within 2 miles. So it's saying you must climb at this rate in order to avoid getting too close to this one, or getting closer than you already are. This aircraft will have a similar display saying you must go down. And following the accident that happened in Switzerland, where 2 airliners collided because one pilot was obeying the TCAS command and the other was doing what air traffic said, now every pilot in the world knows that you do what TCAS says first and you tell air traffic afterwards. And this is a great device because it gives you an awareness of what's happening around you in your aeroplane. Actually, some pilots would contend that they can fly without air traffic control these days. This is also associated with an audio alert, so you get a climb in your headsets just in case you were worried about what to do. Those transponder stuff, now using satellite navigation, we can pulse information out to the ground without them needing a big expensive radar. I installed a new radar at Wharton when I was working there. It cost me £7 million. And so other aircraft can now get information, but more importantly, air traffic can feed information to the aircraft itself. This means that when this is all enabled, next gen is a US term, then we can do away with the radar requirement. That means we can bring the separation down. That means we don't need to fly down those airways, providing we've got some other mitigation for the non-airway traffic or the non-airliner traffic. It means that instead of doing funny doglegs to get from takeoff to landing, we can now go in an almost direct route. It means we can peel in much closer to the airport rather than having to wait in holds. It means that we can know what speed we should be flying immediately after takeoff in order to make our arrival slot in Rome, rather than arriving at Rome and then waiting 15 minutes because we've arrived there too soon. So it's shorter, faster, more efficient, because the less time we spend in the air, the less fuel we're going to burn too. It does raise an issue for those aircraft that aren't equipped, so the military will still be using radars to make sure that the Russians haven't impinged on our airspace again. And while we're on environment, we ought to talk about the weather, which has a major impact on what we do in aviation. The aviator's defense is good forecasts, particularly of thunderstorms and jet streams, which carry all sorts of unpleasantness when we're en route. And we do that through a pre-flight brief, which is really very detailed. It shows us where the uncomfortable flying is going to be, which is why when the captain says it's a nice flying day, what it actually means is the forecast says there isn't any turbulence in the area we're going through. We update what we're hearing en route so that we know that the forecast, or we can see that the forecast and the real weather begins to develop in the same way, and then we update ourselves just before landing so we know exactly what it is that we expect. Thunderstorms are an issue, and we have a weather radar to protect ourselves against those or to find a way through. Very schematic, but you can see here route A from the airplane to destination is the obvious, operationally quickest way through. And we're going to have a very uncomfortable time if we do that, because we'll be getting the worst of the turbulence and the hailstones and everything else. So we're not going to fly route A. Route B looks okay because we could squeeze through there, but actually you never know if there isn't another cell building up. And this is a very dynamic situation. Thunderstorms just don't present themselves as, here I am, here I'm going to stay. They present as a developing feature that you then have to almost double guess what's going to come up next. We can do that to some extent. So here, we'd actually tilt the radar, our aircraft radar down and say, it looks like there's no cell building underneath, or there may be a cell building underneath. So we'll discount B because there might be a cell there. Route C looks pretty good because it's all green only. So I should say this means there's no rain whatsoever. This is a little rain, this is lots of rain, and this is too much rain to even contemplate. Essentially, the radar detects rainfall, and by that infers where the major cells of a thunderstorm are. Because these things are very close together, that means that there is a real shear in the atmosphere, and that will give us all sorts of turbulence, so that's not a good option. Flying round route Delta, route D, is the best option, but you can see that that's going to make us late, and it may run us out of fuel before we get to destination. So you have a continual balancing concept, having detected it, put the seatbelt signs on, looked at the route that's going to be best. If you're taking a very unpleasant route, because that's the only option that you have with the fuel remaining, then you have the cabin crew strapped down and the trolleys strapped down as well. Thunderstorms can also happen at the airfield. And one of the things that happened a lot, but we hardly ever hear of these days, is thunderstorm generates a terrific downdraft of rain in the first instance that then sucks the air down with it. So the air that comes down flows out in all directions. And for an airliner approaching a microburst, as this was called in the States, you get a sudden increase in airspeed, to which your immediate response is, oh, I'm going too fast to land, I shall pull back the throttles, so I go slower. And then you get a sudden reduction in airspeed as your momentum takes you into a tailwind, and then the aircraft crashes. And that happened in the States, where the thunderstorms tend to be bigger than they are in Europe, and in other parts of the world near the tropics on an almost regular basis. Nowadays, the aircraft carries something that will detect the wind shear. The airfield carries a radar that will detect where these things are and where wind shear is apparent, and will warn you, well, pilots are also told, you don't make an approach to land underneath a thunderstorm because of all of these things. So you carry additional fuel if there are thunderstorms forecast, so that you can hold off for a period. Other hazards? Are there any Icelanders in the room, please? Right. This was Eyjafjallajökull plume in 18th of April. I think Eyjafjallajökull, yeah, that's right, in Iceland. This is the disruption it caused in terms of where the ash went. And that effectively obliterated air transport for a large part of Europe for a significant period. And people are going, oh, this is unacceptable. Just remember, when the engine manufacturer designs and tests his engine, he doesn't put it inside one of those to make sure it still works, which is why almost all air traffic was grounded, because we didn't know what was going to happen. Subsequently, a lot of work has been done to try and define those things a little bit more clearly. The Met Office at the beginning of this month announced that they've just introduced LiDAR, which effectively is a laser that works like a radar, that will look at particulate content of the atmosphere. They've got, I think, 8 fixed stations, 1 mobile station in the UK, so that they'll be able to forecast more accurately what the content is and its location, so that the CAA can approve flying within the area sooner, or EASA can do the same. So we are getting better by understanding. But if you don't have that understanding, you're now going into an environment that you have no understanding of, and that's not how you do aviation safely. So if you're held on the ground because of volcanic ash, you should be very thankful that you're held on the ground because of volcanic ash, because that was the safe choice by the airline. Other hazards, birds. The airports go to great lengths to try and keep the birds down. See the long grass here? That's deliberate. Birds don't like landing in long grass to feed because they can't see the predators. So the long grass policy is a way of trying to keep birds from the airfield, and you deter them with sound and with hawks and with all sorts of things. That's what happens if you hit a goose at about 450 miles an hour. It comes in the front and it goes down through, takes out all the electrics, wraps itself around, or the remains wrap themselves around the leg of the pilot in the front seat. That was my first Mayday call. Nobody noticed in the media. Everybody noticed this one, though. This was a flock of geese disabling both engines, and Captain Sullenberger was quite rightly recognised by the media. He's faced with a situation where he's just got airborne, neither of the engines are now going. He has no options. He can't get to any of the airports. So he makes the plan and he chooses the least unpleasant option, which is, I will glide to the river and I will ditch there. There's no drill for that. There's no emergency drill in the airplane for what you do if both engines stop. There's no drill for gliding. There's no drill for landing on water. Well, actually, sorry, there is. There's a bit of guidance and there is a drill to make sure that you close off some of the valves for ditching. So there is a drill for ditching. He did all of that in a very short time. Everybody on the aircraft was almost entirely uninjured, in fact, unharmed. Actually, most of them were completely uninjured. That's 155 people. Save because the pilot had skill based very much on his ex-military experience and his work as an accident investigator. So that was quite important that there was a pilot on board that aeroplane that day. We have some unnatural hazards. People like, and aviation is not alone in this, railway drivers have the same risk where people try and blind you with a laser as you're coming into land. The UK have just formed an intergovernmental group to try and tackle this. That will, and the reason that's happened is that we've just had 2 pilots with permanent eye damage caused by lasers. And that will look at what the police reaction might be, what the law might need to be, and what procedures we might need in order to make that better. So there are some other hazards out there. Now, that was environment, so I'm going to move on to safe crew. I'm about halfway through, but this is the most important part of the presentation. It costs you about it costs you about £100,000 to get a license if you start from scratch and you're self-funding. And it's best that you go to a school that checks that you've got the aptitude to pass before you start. If you go to a school that doesn't test you, then the Honourable Company of Air Pilots run an aptitude testing scheme using the RAF's equipment, actually, that will give people an indication of whether or not they're likely to make the grade. Having got the license, you've now got to spend, particularly if you're self-funding, between £10,000 and £20,000 to get a type rating on an aircraft type. And that will be done with computer-based training, which is interesting. But it means that there's not a lot of personal interaction going on here to make sure that you really understand, as opposed to can pass the tick test. Simulator training, and then a test in the simulator, and then some aircraft-specific training. And if you do all of that, you are now into a 6 to 12 month, every year, reevaluation in the simulator, retraining, and checking, and checking, and checking, and checking. Actually, pilots are probably one of the most checked people in the world, more often than doctors, more often than lawyers, more often than, as far as I can recall, anybody else. So that is a continual activity. But we noticed that there was a downside to some of this computer-based training and things. Over the years, since the Wright brothers first flew, everybody was worried about technical failure. Nowadays, technical failures are few and far between because that design process and the specifications are really good at capturing things that might hurt you. So human error started to dominate in the accidents. And one of the solutions to that was to automate some of the stuff in the flight deck. Let's put in autopilots. Actually, they've existed a long time, but they've got even more complex. Let's put in an auto throttle so the computer can do the work while the pilot just makes the decisions. And that was really good. And the first thing that happened was that all the airlines noticed that their accident rates were going down. Great, it's done exactly what we wanted. So they mandated that the pilots must use the automatics and mustn't hand fly. So when the automation failed or switched itself off as it was designed to, on a dark night, stormy over the middle of the Atlantic, the pilots found that they weren't able to actually cope with that failure. It wasn't just Air France. There was a similar accident in Canada where the autopilot disconnected and the pilots were not able to regain control of the airplane. So all of this great automatics that made it much safer, suddenly presented us with a problem. And that therefore gives you the question of, does that mean that we put more automation in? Let's get the pilots out of there completely, then there won't be any human factor accidents. Or do we put more manual handling practice into the training programs? And this has been a live issue in aviation in terms of it's a live worry until very recently when a number of the regulators said, yes, we will institute upset training and upset recovery so that pilots understand how it is that they need to behave when the automation fails. So we now have additional training because of the automation that was brought in, and everybody thought automation made the pilot's life easier. Actually, it made the pilot's life more complex in a different way. So now we have that particular loop. We think we have a route to solution. And we get checked every 12 months, or if you're as old as me, every 6 months by the doctor. And we do all sorts of other training. So the cabin crew, when they say we're here for your safety, they really are. They're trained in first aid. They're trained in using all the emergency equipment. They're trained in firefighting on the aeroplane. And everybody on the aircraft crew, and this will extend to the ground crew as well these days, will go through crew resource management training, which is looking at the human aspect. So it's, if you like, it's the tree-hugging side of the job. It's looking at the human aspect and understanding how you get the best out of each other and how you don't make human errors yourself or how you trap them. A lot of this training is looking at previous accidents. What went wrong? How could it be done better? What was the issue? Which is one of the reasons why we see the accident rate coming down year on year. Which leaves me with procedures. And I'm going to do this quite quickly. The flight deck door came in, hit the headlines after a Germanwings accident. The flight deck door effectively eradicated death by hijack. The reason for this graph is that shows the hijack deaths. That was the people on the ground in 9/11. But after that, in the decade 2010, 0 deaths from hijack. Didn't quite eliminate it. The door was hated by the crews because now you couldn't talk to the cabin crew. The cabin crew couldn't talk to the flight deck directly. You couldn't do the normal human interchange of information. So we had to find a procedure, or a number of procedures actually, to work around how we worked the door when it was closed, how you spoke to each other. If you're on an airliner, you'll hear bing-bongs going off lots of the time. That is actually the interphone language. It's I need to talk to you, and it will usually be bing-bong, is the coffee ready yet? I probably shouldn't say that. It'll also be bing-bong, Captain, how many minutes have we got left before top of descent? So because I need to get other stuff sorted out. Procedures: remove uncertainty, coordination, familiar sequence, trigger events. If next time you fly, if you're close enough to the door where you walked on and you hear it clunk, you'll notice that just after that, the captain will make his first PA, because he knows that when that door closes, the cabin crew will not start their safety brief for a little while. So they close the door, they know that he's going to say something. When he said something, then they'll start doing their next bit. When he starts the engines, they'll start giving the safety brief. And all of these actions within the crew, even with that door in place now, are done without anybody talking to each other. Trigger events mean that you know precisely what goes on. And the same thing happens on the flight deck, where where the two pilots will be doing things according to certain trigger events. So you get as minimum talking as necessary. Below 10,000 feet, everybody operates a sterile flight deck. The only thing you do below 10,000 feet, takeoff and landing, is talk about operational stuff. You can't talk about anything else then. Checklists, of course, are the ultimate in sort of trigger and sequence. Ignore the picture. But it does show how few checks you need to operate a advanced fighter. That's from sat in to shut down, which was much easier. Aerodromes also have procedures. They make sure that the routes in and out of the airport, SIDS, standard instrument departures, STARS, standard arrivals, are safe for all the aircraft that are going to use the airport, even when they've had, for instance, an engine failure. So your single engine failure is not a catastrophic event. The management then makes sure that everything's done to keep that tight. ALART means as low as reasonably practicable, because in the real world there is no such thing as 100% safe. Even getting up in the morning is not 100% safe. They will understand what aggravates their risks. They must understand what makes those risks, or what mitigates the risks. And they'll use a safety management system usually where the first page is signed by the chief executive officer of the airline that says, this is what I do, and then goes on to say, these are the people named by name with the responsibilities for safety in the airline. It'll cover their risks, it'll look at how they mitigate their risks, it'll look at how they maintain and improve safety by monitoring, reporting incidents, investigating incidents, and then correcting incidents. When the regulator says a pilot must fly no more than 900 hours a year, for the operator that means I must program him for no less than 900 hours a year. So there is always a bit of a tension there. Equally, if the regulator says you must give the crew 10 hours rest, the operator says I must always ensure that the crew have no more than 10 hours rest so that I get the most out of them. And that's because they're under commercial pressure. Commercial pressure that has led in some instances to strange contracts like pilots paying to fly, paying the airline to fly, in order that they could build hours to improve their attractiveness to some of the higher, if you like, airlines further up the chain. There are airlines that everybody wants to work for, and there are airlines that everybody transits through to get to those airlines that everybody wants to work for. The Danes are now leading an activity looking at pilot contracts for EASA, because to try and understand what that really means. They're just they're great commercial ideas. They don't always make as much sense as we would like. Business models as well. In the good old days, let's take British Airways. It's based in Britain, its aircraft fly from Britain, its main operating base is Britain, is regulated by EASA, but by the Civil Aviation Authority. So everything's done by one regulator, and everything is sort of ties up to one set of rules. Then you get another airline that will be based in one country with its aircraft registered there, and then it will do most of its flying from another country. And we've just seen a third airline that's come up that has its headquarters, its aircraft operating base, the state of registration of its aircraft, and the country that it flies most from, all different. There are very good commercial reasons for doing that, and I'm not saying that it's wrong, but it's unusual, and with lots of different regulators involved at that point, or regulatory authorities. EASA are now looking at the implications that new business models could have to try and trap it. Management, final bit, we talked about just. There's developing work. Lamb and Clutton did some work for actually the health and social care sector, showing that the way that you really get safety into an organisation is by bringing all of those things on the left-hand side together. So a just culture, open reporting, learning and informed. It's the sort of culture that we'd all want to be working in, I think. So, very quickly, I'm not going to give you statistics in terms of percentages or anything else, because you can never be 25% dead. But I did find an airline. I fly with this airline quite often. I like this airline. I feel safe with this airline. These are the accidents that they've had since 1970. You can see that all the deaths happened before 84. They've had a recent accident. Actually, the one at the bottom was a few days after the Germanwings accident, but didn't make the press. That's still under investigation, so I can't talk about it. Those with asterisks I'm going to look at briefly, because that's where we get our lessons from. The first, electrical problems, toilet fire. A fire in the toilet brought this aircraft down. It was landed safely, but half of the passengers on board died from the smoke and from the fumes. And as a result, regulations around the world were changed very quickly, putting in smoke detectors, banning smoking from the toilets, and giving the cabin crew better firefighting training. and equipment so that they were actually able to do what people thought they'd have been able to do. And some airlines even put on their safety card in the pocket in front of you an indication of what that emergency lighting on the floors is intended to do. Next accident, it's called the Gimli glider for various reasons. This is an interesting one. It's some time ago, so don't get worried it's going to happen to you tomorrow. Fuel gauges didn't work, aircraft still cleared for dispatch, providing you know how much fuel there is in the tanks. That's actually acceptable, providing you don't put the amount of fuel in pounds instead of in kilograms and end up with half the fuel. Both engines stopped. Air traffic are trying to glide them to one airfield. The captain's an experienced glider pilot. The co-pilot is an experienced military pilot who works out very quickly that they won't make the airfield they're being vectored towards, but remembers that he used to fly from an airbase that's now disused, that's in this vicinity somewhere. So air traffic changed their steering. He doesn't know that that airfield has got half a runway, it's disused, and there's a race in progress on the other half of the airfield. The captain side-slips the aircraft, which is to lose height to get into the place. No serious injuries. Because, again, the first thing they did when the second engine stopped was look for the drill. There wasn't one. There is now. Every large aircraft I've flown has a no engines checklist for this sort of reason. Gimli glider. Some of you will understand which country and probably which airline this is by now. A little bit more recent, 2008, the first officer is behaving strangely. He left the flight deck, went to the loo, came back, and was behaving sufficient to alarm the captain, who got the cabin crew to remove him from the flight deck. This is important. We have two pilots on the aeroplane in case one becomes ill or incapacitated. And our medical looks at, to some extent, are you going to suffer an incapacitation event? Not perfect at doing that, but two pilots means that the chance of both of them dying on the flight deck on you is pretty remote. But this did bring a new, or rather this one comes into consideration when we think about the Germanwings accident that I'm going to cover very briefly. This is the Germanwings accident. The French, when they investigated, found 6 other instances of what they thought was pilot suicide murder. One of those I discount because there was only one pilot on the aeroplane, and I don't think that's in the same category. Interesting thing to note is that a number of these happen with 2 pilots on the flight deck. So it isn't the door that's the issue, and a number of them happened before the door was there, so it isn't a door issue. But it is an issue of what we do with our pilots. The thing to remember is that pilots are, much as we would hate to admit it, normal human beings. And we're subject to the same stresses as everybody else. And while there's a downside to having a pilot on an aeroplane, there is a much greater upside. I've mentioned 2 of those accidents and didn't need to think really to identify 2 further to bring that number up to a larger number. Hands up all those who've flown in a civil airliner as a passenger. Hands up if you... Okay, now put your hands up if you read the card in the seat back in front of you. Good. Brace position. We all do this, don't we? We sit like this. If you do that, you will end up with 2 broken hands when all the stuff comes out of the overhead bins, and you won't be able to release the seatbelt. And if there is a fire, the smoke will kill you. If you do that, which actually some cards try and indicate, then you will have one good hand to get the belt out of the way. If you put your feet, as it says here, so that they're locked so they can't swing forward into the aircraft, into the seat in front, you'll have 2 legs. If you don't do that properly, you'll have 2 broken legs, and you won't be able to get out even if you can get the seatbelt off. Getting your head beneath the height of the seat in front of you is the first protection. Getting your hands right is the second, and getting your feet right so that you can get the seatbelt undone, get out of the aeroplane, are the fundamentals to safety. And this gets proven every time there's a hard landing, and actually the first indication came out of the Kegworth accident, where there was no fire and it was easy to analyse injuries. So please read it. Please know where the nearest exit is. I always do. I always read the card because the doors change. I don't ever want to be at a door and not know how to open it in the event that I need to. I actually profile the passengers around me as well. Go, that's the way I'm going to go because there's nobody bigger than me in the way. Quite seriously, all of my mates do exactly the same thing. If you've been involved in aviation long enough, you do everything to improve your situation as much as you can. Okay, stats. Years down the left, number of accidents worldwide down the middle. All of them ICAO apart from the bottom line because they haven't released their 2014 report yet. And world deaths, accident numbers, number of deaths for all aviation. This is cargo and passenger transport. And you can see that there still has been a tremendous improvement in the number of accidents. Only 21 last year. Big blip in the number killed because we had two major aircraft, MH17 and MH370. One shot down and one disappeared. Happened in that same period. The Flight International figures, they show that 3 scheduled, 4 commuter, and 12 non-passenger. But they exclude different aircraft because they've excluded the MH17 shoot-down because they say, well, MH shoot-down wasn't an aviation accident, that was an act of something else. So for us, we'll go, well, actually, that should have been 4. 4, 4, 12, and the one that's missing is the air ambulance because they didn't include the air ambulance either. To put that in context then, we kill more people on the roads in the UK every year than the international, more or less, than the international aviation activity does around the world every year. And we kill we kill more pedestrians in the UK. So it isn't about driving, it's just being a pedestrian. If you're a pedestrian in the States, they kill 4,000, and they don't walk anywhere. They kill 4,700 people in 2013. And every year, actually, that figure's not changed very much. Compared to the numbers that we see in air transport, I think that, and people will talk about, oh, well, I don't fly every day. That's people flying every day. That's an aircraft getting airborne every second. I'm over 45 minutes in now, but over 2,700 aircraft will have got airborne in the period that I've been speaking. Last year, there were 8 fatal accidents occurring in aircraft carrying passengers. Now, I reckon that's better odds than buying a chicken from a supermarket. So I hope those of you that were nervous in the first instance are reassured. Any questions? Interesting.